So the first speaker of today is Professor Saeed Tafazolian from IMEC Unicamp, and he'll talk about uncertain maximal curves. Please, Saeed.
Hi, everybody. Good afternoon. First of all, many thanks for the organizers to give me this possibility. Today, when I wanted to prepare this presentation, I remembered an old message. I mean, in May of 2018, I have received the following message from Guilherme Piziotti with this title: Sugestão encontro Fernando, Corpos Finitos, Curvas e Semigrupos. I have put the translation here. No ano de 2021, mais precisamente no dia 22 de junho, o Fernando fará 60 anos. Sei que ainda está longe, mas gostaria de sugerir um encontro ou evento para homenageá-lo. These days, we are all gathered here in honor of Fernando Torres. We are holding this meeting, but unfortunately, without him. This is very sad. Today, I want to speak about some work that I have done with Fernando Torres. Let me to review some terminology and notations. The word curve, we mean projective, arithmetical, non-singular algebraic curve, and when we use the word C be a curve of genus G defined of a finite field with Q elements. There is a beautiful result due to Hasse and Weil, which is called the Hasse-Weil bond, that give us some information about the cardinality of a number of rational points of curve over finite field. I mean, this cardinality satisfies in these inequalities. And for some applications, for example, in coding theory or finite geometry, we are interested to find some curves with many rational points. In particular, here we are interested to find curves over finite field that this number attains the upper bound. So suppose K is a finite field with Q square elements. A curve C is called maximal over K if the number of rational points of C over Q square is equal 1 plus Q square plus 2GQ. About the maximal curves, there are several problems. For example, about the general possibilities. There is the first result about the possibility of a genus of maximal curves due to Ihara, which say that suppose C is maximal over FQ square, then the genus of C, I mean the genus of a maximal curve over a finite field with Q square elements is bounded by this number. And there are also results due to Rook and Sistenos that classify curves, I mean maximal curves of over FQ square with this genus. I mean, they have shown that there is a unique maximal curves over FQ square which attains the above genus bound, and it can be given by the affine equation yq plus y equal x q plus 1. This is the so-called Hermitian curve over fq square. The first problem that we can think about is the spectrum of the genus, and then the possibility, the classify the maximal curves of a given genus, and also for another application in coding theory, sometimes we need to find some equation for curves. To find explicit curves. Here, there is the problem suggested by Saeed. If we define the M of Q square, the set of all numbers G, such that there is a maximal curve over Q square of genus G, and then determine the M of Q square. Today, we know that there are many results about, to determine this set. Rapidly, I'm interested to review some of that. The first one, that the result by Ihara that I have said. Then again, there is the result of Rook and Stenos that I have announced. And there are another result by Fernando and Fuhrman that say there is gaps in this interval about for the genus of maximal curves. That is, I think, the first result of Fernando about the maximal curves. And for the small finite field, this set is not, for many small finite fields, the set is determined, but for another one, for example, for M of 64, we don't know, at least I don't know if there is a maximal curve of genus 5 over finite field with 64 elements. So I wanted to say that up to now, there are several results about the spectrum for the genera, but there are also some open problems. Okay, this is another question that we have asked. If we know some elements, some numbers of MQ square, that means there exists some maximal curves. But how we can construct this maximal curve? This is another question which is not very easy. Then today I want to speak about this problem. But how can we construct a maximal curve? There is an essential result due to Saeed or I don't know, John Tate or Kleiman, that say if there is a morphism defined over the field K between two curves C and D, then El polynomial of D divides the one of C. El polynomial, by El polynomial, I mean the characteristic polynomial of the Frobenius acting on Jacobian of the curve. In particular, a subcover D of a maximal curve C is also maximal. So one way to construct a maximal curve is put here Hermitian curve and find all curves which covered by Hermitian curve. For example, if M divides Q plus 1, then the following curves are maximal over FQ squared. It's not difficult to find some morphism between the Hermitian curves and each of them. Okay. In fact, in Arnaldo Garcia and Finitos and Xing, in this paper, give some ways to find subfields of the Hermitian function field. But in this paper, they tried to show the existence of maximal curves of given genus. And after this paper, many people try to find all subfields of the Hermitian function fields, or for many subgroup of automorphism of Hermitian function fields. They try to find some possibility for the genus of maximal curves, but sometimes without giving any explicit equation. But as to determine the number of rational points of a explicit curve is not very easy. So it is not very easy to construct a maximal curve. But there are some family of maximal curves. Some family of curves that we know we have. Some properties. For example, Artin-Schreier extensions of rational curves, or Kummer extensions, for example, which these properties help us to calculate the number of rational points of this type of curves. Here, I'm interested to speak about the Kummer extensions. By Kummer extensions of a rational curve, I mean a curve. A affine curve given by some equation such that yn equal fx, where fx a polynomial with coefficients in fq squared. More or less, all maximal curves which we know of this type have a simple polynomial in this site. For example, curves given by this equation, yn equal xm plus 1, or yn equal xm plus x. Clearly, we know that the Hermitian curve is a curve of this type. For example, here, if we put n equal m equal q plus 1, we have a Hermitian curve. Or in this family, if we put m equal q and n equal q plus 1, again, we have the Hermitian curve. The first work that I have done with Fernando, it was to classify this family of curve, and we have shown this family of curve is maximal of fq squared if and only if n and m divide q plus 1. And in another paper, we tried to classify all maximal curves given by this equation. Okay. Garcia and Sistenos, in this paper, they studied Chebyshev polynomials and construct some family of Kummer extension related to Chebyshev polynomial. Let me to review Chebyshev polynomials, and I want to say that with Fernando, we have tried to generalize the result of this paper and try to find some Kummer maximal curves. Okay, Chebyshev polynomials or Dixon polynomial of the first kind with parameter 1. We know there is an elementary problem in high school which asks us to find some relation between the xm plus x minus m and also x and x minus 1. But we know there exists a Munich polynomial of degree m, I mean phi m, with integer coefficient such that relate these polynomials. I mean, for a Chebyshev polynomial of degree 1, we know that phi 1 of t equal t, phi 2 of t equal t square minus 2, phi 3 of t equal t 3 minus 3t. And when n is a huge number, we don't know any idea about this polynomial. But at least we know that this polynomial is a polynomial of degree m. Here, there is a recursive formula for Chebyshev polynomial. I mean, using Chebyshev polynomials of degree m and m minus 1, we can determine the Chebyshev polynomials of degree m plus 1. In the book of finite fields and applications, we can find several properties of this family of polynomials. Okay, as I said, in this paper, Arnaldo and Henning tried to find some maximal curves using Chebyshev polynomial. We tried to generalize the result, and in this paper, okay, with my ex-PhD student Ahmed Kazim Fard and Fernando Torres. First one, we consider the simple case. I mean, instead of fx, we put this Chebyshev polynomial, and we consider this curve Vn equal phi m u. And for some conditions, for example, when n divides q plus 1 over 2 and m divides q or minus 1 over 2, or m divides this number, then this curve is maximal over fq squared. I mean, the proof is not difficult. Only we have tried to show this curve is covered by the Hermitian curve. Rapidly, I explain this morphism. I mean, if we put q plus 1 equal 2 nt and q plus 1 equal 2 ms, then we consider this morphism, and using some calculation, we can find this curve is covered by Hermitian curve, and so by these conditions, this curve is maximal. But this is the simple case. Another type of Kummer extension using Chebyshev polynomial. Consider the following conditions: or n and m divides q plus 1, or n divides q plus 1 and m divides q minus 1. In this case, we have this family of maximal curves yn equals phi mx plus 1, where phi m is a Chebyshev polynomial of degree m. By these conditions, this curve is also maximal over fq squared. Clearly, here we consider the Chebyshev polynomial plus 2. And I want to say that it's very important, this plus 2, because when we consider this sum, we can find some decomposition for this polynomial. And it is very easy to see that this curve is not isomorphic to the last one. Okay. We try to find another conditions for, to construct maximal curves. For example, consider two numbers m and n, which are related by this equation, m equal nd minus 2l. And then, if d is even and nm divides q plus 1, then the following curve is maximal over fq squared. Again, always we try to find some covering map between the Hermitian curve and this one. Another one, here we consider if d is even, but if d is an odd number and nm divide q plus 1, then we have the following families of maximal curves. Here we have these curves, and here we have another family of curves. Here we have another polynomial, which is not a Chebyshev polynomial, but is related to Chebyshev polynomial. As I said, when we consider Chebyshev polynomial plus 2, we have some decomposition for this polynomial. We put here this polynomial. Again, by this condition, we can construct another families of maximal curves. And okay, in particular case, when L equal 1, here, then if m equal dn minus 2 and q is congruent m plus 1 module nm, then we can find, because here we can consider 5 or 6 cases, different cases depend on d and m is even or odd. We can find several family of maximal curves. And I pass from this page. Okay. Another result related to Chebyshev polynomial, which we found in that paper. This is a theorem. Arnaldo and Henning in that paper, for some number m, using the maximal curve, they have shown that the I think, yes, if m, they have proved, if m is a divisor of q plus 1, then the Chebyshev polynomial of degree m is a separable. It's separable. But we generalize the result. We have proved this beautiful result. If I've said beautiful because nobody know about the separability of the Chebyshev polynomials. If we have a Chebyshev polynomial of degree m, where m is co-prime to the characteristic of the finite field, then this polynomial is separable. And to prove this result, only we have used some classification of Kummer maximal curves. Okay, up to here, we try to find some sufficient condition to construct the maximal curves. But what about necessary condition? And how we can classify a given maximal curves given by Chebyshev polynomial? Here, there is a joint work with Professor Yaptab that we try to find some classification for hyperelliptic curves. I mean, the first one, it was this result. Consider, I mean, let D be an even integer, and let Q be a prime power, which is co-prime to D. Then the hypertrophic curve C corresponding to this equation, I mean, y squared is equal x plus 2 multiple phi dx. Here, phi d is a Chebyshev polynomial of degree d. Is maximal over fq square if and only if either satisfy this condition or this one. Here, I'm interested to explain the idea of demonstration. In fact, excuse me. Yes. In fact, consider this curve, this hypertrophic curve, y squared equal x to d plus 1 plus x. The main idea is to decompose the Jacobian variety of x up to isogeny of fq squared. In fact, we consider this involution of x, and we have shown the quotient of x by this involution is exactly this one. And also, we can show that the Jacobian of x is isogenous to the Jacobian of the curve C square. So this implies that the L polynomial of x equal the square of L polynomial of C. So the curve, this curve is maximal if and only if this curve is maximal. And many years ago in some paper, I classified these curves, and I have found this condition for maximality of x. So when d is a even integer, this curve is maximal over fq squared if and only if satisfies these conditions. Okay, it was for when d is even integer. We have the similar result when d is an odd integer. I mean, when d is an odd integer, we can consider this curve, y squared equal x plus minus 1, 2 phi dx. Then this curve is maximal over fq squared if and only if 2d divides q plus 1. To prove this result, again, we repeat the last argument, except we use this curve x. I mean, we try to decompose the Jacobian of this curve x up to isogeny, and we prove that the Jacobian of this curve is isogenous to the square of Jacobian of the curve C. And again, we have proved this curve is maximal if and only if this curve is maximal, and we know that this curve is maximal if and only if 2d divides q plus 1. In that paper with Yattap, we tried to find another result also. I have put only some of one. For example, here for d, I mean for even integers d, we can consider another family of curves. For example, here y squared equal x squared minus 4 multiple phi d. Here phi d again is a Chebyshev polynomial of degree d, and we proved that these curves, the maximality of this curve, is equivalent the maximality of this curve, and this is equivalent to this condition. And I mean, we have tried to classify this family of hyperpletic maximal curves. Okay, there are another result, I think, for odd integers also. We tried to find some result that if one is interested can see in that paper. Okay, here I'm interested to review a result for others, which is related to Chebyshev polynomial and maximal curves. For many years, people expected that all maximal curves covered by Hermitian curves. But by GK curves, I mean the curves constructed by Professor Korchmaros and Giulietti, we know that there are some curves which are not covered by Hermitian curve. But I remember sometimes Fernando accepted that all plane maximal curves are covered by Hermitian curve. It was some conjecture of him. And the first equation, the first problem was how we can determine all plane maximal curves, because up to that time we know we have Fermat curve, which is a plane maximal curve. I mean this one. This is maximal if and only if m divides q plus 1, and we know that this one is covered by Hermitian curves, and also Hurwitz curve, which is another plane maximal curve that for these conditions, for maximality of curve, this curve also covered by Hermitian curve. I remember Fernando asked if there exists more plane maximal curves, which is not isomorphic neither Fermat nor Hurwitz curves. There is a beautiful result due to Nazar, Rivelto, Pietro, which have shown that yes, there exists a small plane FQ square curve C such that neither a Fermat curve or Hurwitz curve is isomorphic to C. I mean, they considered this curve, and they have proved this curve clearly is a plane curve, and it is not isomorphic to Fermat or Hurwitz curve. And for this condition, this curve is maximal. Okay. Here, I want to say that in the last work that unfortunately we couldn't finish with Fernando Torres, we tried to find some classification about the similar to the result we have found with Yaptap for general curves, but unfortunately we couldn't find. Only I'm not sure if we have proved this result or not, but I think the plane curve yd equal phi d, here phi d is a Chebyshev polynomial of degree d, is maximal over fq squared if and only if 2d divides q plus 1. But I'm not sure today if we finish the proof of this result or not. Okay, at the end, I would like to dedicate a poem, a Persian poem, to Fernando Torres. This poem due to Saadi, a poet is a Saadi of Shihaz. A man who is remembered with goodness and kindness will never die. Dead is the one who is not remembered with goodness and kindness. Okay, thank you for your attention.